Okay, so again, page 359. Get things organized here. Okay. So, first thing we're going to look at, okay, on this section is identifying the perpendicular bisectors of a triangle. And so our essential question is, how can you use perpendicular bisectors to find the point that is equidistant from all the vertices of a triangle? All right. And so we are going to, well, we'll skip that explore because we'll do it ourselves here in a little bit. Okay. Oh, I actually just want to do one though here first. Let's see. That's kind of upsetting. They did it for us already. Well, let's just do it here on our own. Okay, so in our little white space you've got here, sorry, on page 59, we'll use some of this white space right here. Okay, what I would like you to do is to draw a triangle in this like white space right here. Okay, and so you can kind of get an idea about what we're going to be doing if you look at that step right up there. But let's go ahead and just do it ourselves for some practice. And I'll call this, I don't know, I'll call this XYZ, triangle XYZ. Okay, you don't have to draw your triangle, exactly like mine if you don't want to there. Okay. So, let's construct a perpendicular bisector for one of the sides of our triangle here. And you can pick any side you want. I'll do XZ, this side right here. Okay, you can pick any side you want. So I'm going to turn. I like to turn my paper so that like is kind of horizontal. All right, you don't have to turn if you don't want to. Let's go ahead and do that. So again, perpendicular bisector. Kind of ignore segment XY, ignore segment YZ for right now. We're just going to focus on XZ. I'm going to take my compass, right? Compass point on the end point of this segment. Again, XZ, compass point right here on the end point. Okay, oops, place it down there. Make sure I'm open more than halfway. I think I'm okay with that. And then I'll just draw my arc there. Okay, and I'll do the same thing from point Z. Okay, without opening or closing my compass, I'll drop my point down. I'm going to have to do this left-handed, I think. This is not going to go well if I do it that way. Let me do it this way. So a little football there for side XZ in my case. And then we'll draw that perpendicular bisector in. Okay. I like to erase back some of these arcs just because, like, erase them away a little bit. I'm going to leave where they intersect there so I can still see that, but I like to erase back some of the other stuff because we're going to be doing a lot of other little arcs in here too, and I don't want to get confused by stuff if I can avoid it. So, if you don't want to erase them, that's fine. You can leave them if you think you can keep track of everything, but I'm going to erase them back. Okay, so there's one of my perpendicular bisectors there. All right, I'll turn my paper and do another one here. So let's just pick another side. You can do like segment like YZ there. You can do segment like YZ. Okay. So then, again, I'll adjust my compass just a little bit, move things in slightly. there's my other two arcs. Again, I can see where it intersects right here and here. It gets a little bit confusing with all the different arcs going on, so try and be careful. Keep track of where things intersect and stuff. Okay. Now you can see my two perpendicular bisectors, they intersect. Right, so there's one right there, there's the other one. They both intersect right here at this point. Okay, right at that point, right there. I'm going to erase back the little arcs here that I had for that most recent perpendicular bisector. And then I'll go ahead and do the perpendicular bisector for the third side. Okay. And we'll see what's going to happen here. So I'll do my last side here, segment XY. And when you got all three of your perpendicular bisectors drawn there, hopefully you will see that they all three intersect at the same point. Okay. And as it turns out, this is true in general. Okay, this will work for any triangle, no matter how you draw the triangle, whether the point is obtuse, whether the triangle is obtuse, acute, or right. Okay, you can expect to see all of your perpendicular bisectors intersect at the same point. Now, did anyone have, so my perpendicular bisectors all intersected outside of my circle. Sorry, outside of my triangle. Okay, did anyone have their perpendicular bisectors intersect inside the triangle? Okay, so how might we describe my triangle here? By its sides, for example. How might we describe it? Is it equilateral? I say it looks pretty isosceles to me. I'd also be okay with saying it's scalene. That's fine too. What about by its angles, though? What do you think there? I didn't draw it as a right triangle, okay? I didn't draw it to be a right triangle there. It looks pretty close to a right triangle, but based on what I see here, my point, it's outside my triangle, so actually that's going to tell me that this angle right here is obtuse, slightly obtuse, okay? If you draw like a precise right triangle, your point here is going to end up on the hypotenuse, and for those of you that drew acute triangles, most of those points should then end up being inside, okay? And again, if yours is close or something like that, well, it could just be because you're a little, you didn't draw it precisely. But if we drew exactly a right triangle, if we drew a right triangle, the point would be on the hypotenuse, and then obtuse triangles, your point of intersection is outside, and then acute triangles, the point of intersection would be inside. Okay, so that's something there. But this point has a special property. All right, it has a special property. And it has a name too. So the name of this point is the circumcenter. Okay, circumcenter. Okay, so prefix there, circum means to kind of go around, like to circumnavigate the globe, means to go around the earth, right? That was, I think, like one of the goals of like Magellan or something like that. Okay, those early explorers find a way around the earth. Okay. So this is the circumcenter, but it's the center. It's the center of a circle, okay, that goes around the outside of our triangle. So if you take now your compass and put your compass point on the circumcenter, okay, compass point on the circumcenter, and then if you measure from the circumcenter to one of your vertices, okay, So again, for those of you with like a regular compass, you'll take the compass point, put it on the circumcenter, and then open up your compass to either point X, to point Y, or to point Z. Okay, so I'm going to take my safety compass here and put the circle at the circumcenter, and then I'm going to open and adjust my compass there so that it lines up to that point right there. Okay, you can't really see it, but it's there. And if you draw a circle, of course it's moving because this book is not flat. Let me do this. Make it much easier for me. Okay, there we go. You can see that we create a circle. And what's special about this circle that has a center there at the circumcenter? What's special about this circle? What is it doing? What's special about this circle? Yeah, Steve.
It's touching like each side of the triangle.
Not all the sides.
The angles.
Yeah, the angles are all the vertices. Exactly right. Exactly right. So this circle, okay, it's called the circumcircle. Okay, circumcircle. Okay. So the circumcenter the point located by the perpendicular bisectors of a triangle. Okay. And it is, since this circle hits every vertex, okay, how would the measures compare? So if I measured from the circumcenter to X, or if I measured from the circumcenter to Y, or if I measured from the circumcenter to Z, how would those measurements compare? How would they relate? So again, if I measured from the center to X, from the center to Y, from the center to Z, how would those measurements relate? They would all be what? What do you say? How does the distance from the circumcenter to X, the circumcenter to Y, the circumcenter to Z, how would they relate to one another, those distances? They would all be what? The same, equal, exactly right. Okay, so the circumcenter is equidistant to the three vertices, as Stephen said earlier, right? The vertices there. Equidistant to the three vertices of the triangle. Okay. Equidistant to the three vertices of the triangle. So this point, the circumcenter, is equidistant to X, Y, and Z. They're all the same distance. Okay, because all X, Y, and Z are on that circle. Okay, and the center is that circumcenter there. Okay? So that's the circumcenter right there. Questions on any of that? So this is a result of the property actually of perpendicular bisectors. Okay? When you construct the perpendicular bisector of a particular size, like YZ right here, if you pick any point along this perpendicular bisector, so like just pick a point like right here, for example. This point right here is equidistant to Y and Z. All right? All the points, any point on this perpendicular bisector that you pick will be equidistant to Y as it is to Z. Right? So the distance from this point to Y and the distance from this point to Z are the same. So when we locate the perpendicular bisectors of all three sides, this one point is equidistant to all three, X, Y, and Z, simultaneously. Any point on this perpendicular bisector is equidistant to x and y. Any point on this perpendicular bisector of side xz is equidistant to x and z. And then same thing here for the y and z points. And so then where they all intersect, that's where they're equidistant to all three of the vertices there. Okay? So there it is. All right. So if we go over to, excuse me, the other page here. Okay. We'll talk about the concurrency here of triangles perpendicular bisectors. So I guess there's the circumcenter theorem right there, if you wanted to see it in a different kind of way. The perpendicular bisectors of the sides of a triangle intersect at a point that is equidistant from the vertices of the triangle. Okay, so there's the actual theorem right there. Okay. All right, so there's that. All right, so if you'll turn then to page 361, we'll kind of use these properties a little bit. Okay. So page 361, we're told that we can use the circumcenter theorem to find segment lengths in a triangle. Okay. So we've got KZ, LZ, and MZ. Okay. So these are all perpendicular bisectors. So this, and this, they're perpendicular bisectors of the triangle GH and J. And we're going to use the given information to find the length of each segment, and of course note that the figure is not drawn to scale. Okay, so the figure is not drawn to scale there. All right. So the first example here we've kind of like done, they've already done for us, I guess, so to speak. Okay, so taking a look at that one. Right, we've got that, for example, ZM is 7. So I'm going to do this in pencil because I'm going to do we're going to do letter B here in a second. But ZM is 7, so ZM is 7. That's 7. Okay. ZJ is 25, so Z to J, 25. And then H to K is 20. So H to K right here is 20. Okay. And we're asked to find ZH, so this length right there, and HG, this full length right here. Okay, so that's what we're asked to find. One second, zoom in some, so that way you don't have to like have all this information. There we go. So let's worry about ZH here to start out, right? So ZH, Z remember is the circumcenter, right? And the circumcenter is equidistant to the vertices. So the distance from Z to H will be the same as the distance from what? From Z to what other points? Z to J, for example, or Z to G. Okay, so Z to H is what measurement then? What does Z to H have to be? 25, right? It's got to be 25. If Z to J is 25, Z to H will be 25. And what other segment will be 25 here? We know for sure. Z to G. So this will also be 25. So 25, 25, 25. Okay? And so we get that right there. There it is. Z to J is 25, so Z to H is 25. Okay. What about HG? What will HG be? What's that got to be? It gives you the answer right there. It's got to be 40. But why is it 40? Why is H to G 40 there? Why is it 40? So, Maddie G?
Because K bisects GH.
Good.
And both sides, like on either side, it would be the same.
Right, so if that's 20, this has got to be 20 as well. And so then from H to G, the full length there has got to be then 40. Exactly right. Very good. Okay, yes. So we're not only using the fact that Z is the circumcenter here and it's equidistant to the vertices, we're also using the fact that how do you find the circumcenter? Perpendicular bisectors. So ZM, ZK, ZL, those are all perpendicular bisectors of their respective sides. And so K is the midpoint, as Maddie G correctly identified. So if that's 20, then that's 20 right there too. Okay? So let's change these scenarios now because we've got for letter B there. So I'm going to erase this away. Okay? So for letter B, we've got ZH is 85 now. Okay, MZ is 13. And HG, the full length here, is 136. 136. Excuse me. And so we want to find kg. So what is just kg right there? And then what is zj? And z to j is this length right here. Okay. So, any ideas here? What could we say? Stephen, what do you say?
I said kg was 46.
46? Okay, where'd you get that from?
I did 136 minus 90.
So be careful here now. 90 is talking about a degree measure, right? Is 136 a measure of an angle?
No.
It's a side measure right there from H to G.
Okay.
So we don't want to subtract 90. I see what you're saying. You're thinking like maybe like it's going to be supplementary or something, or yeah. So not quite. We're looking for this length right here. From K to G, the length. So yeah, Jenny?
I said that it was 68.
60, what? 8? Okay, how did you get 68?
I said that 136 divided by 2 is 68.
Okay, so you see that there, Stephen? K to G is going to be half the length of the full length there, 136. And again, that's because KZ, if you remember, is a perpendicular bisector. It's cutting this long segment into 2 equal parts. So if the whole thing's 136, divide that by 2, and yes, you get 68 there. Okay. Right, very good. And then, so what about KJ? What will KJ have to be here? What will KJ have to be? Go ahead, Jenny, if you want. Well, never mind? Okay. What does KJ have to be? Remember, Z is the circumcenter, so it's got to be equidistant to the what? Okay, Z is the circumcenter, so that means it is equidistant to what other points here? What do we say? What does the distance from Z to J have to be here? What's this got to be? Go ahead, Jackson. 85, exactly right. Where'd you get 85 from?
Because zj is equal to zh.
Yes, Zj is equal to Zh is equal to Zg. 85. Maddie G, is that what you're going to say too? 85? Yeah, good. Okay, 85 is the answer there, okay? Very good. Questions on any of that? Are we all just really tired and that's why no one wanted to answer that question? Or are there questions there? Are we all okay with that? Okay. So why don't we go ahead and turn the paper over here. And why don't you guys try number, let me see. Yeah, go ahead and try number 5. Okay, page 362, try it number 5 there on your own. Okay, you've already got the circumcenter drawn and the perpendicular bisectors drawn there. Okay, so go ahead and label things and then solve. Okay, so just number 5, you don't have to do number 6. Just number 5 is fine. Okay. Don't find GK though. Find JH, please. Okay, so find the measure of JH, find the measure of ZJ there. Okay, don't find the GK. I don't think we have enough information there to find GK. I think that's an error in the book. Don't think we had enough information. Yeah, no. So find segment JH, find ZJ as well. Give that a try. Again, make sure you're finding JH, not the GK stuff. Find JH and then ZJ. JH and ZJ. Yes. Don't worry about G. 'Cause I don't know if we know. They look the same, but the problem is, so we don't want to assume that. I mean, I agree, it looks like they should be, but I don't think we can assume that. So we want to be careful. All right, so Anna, what'd you get for the measure of JH? 129. So JH, and how'd you get 129 for JH? What did you do? I think it should be 126 there.
Oh, yeah.
Okay. Okay, gotcha. That's fine. Very good, though. Very good, thank you. And then how about Colin? Colin, how about what'd you get for ZJ? 65. Okay, and again, the ZJ, that's the measurement from the circumcenter to the vertex, which will be the same as Z to G and same as Z to H there. Okay, so these three we know are going to be all equal. Okay, very good. All right, so pretty good on that. We're going to take a look at one more thing here, and that's talking about finding the circumcenter in the coordinate plane. But the good news is finding the circumcenter in the coordinate plane is just like finding the circumcenter not in the coordinate plane, okay? So next page, we'll just do one example here, excuse me, and then we'll move on to the second little topic. Second special center we're going to talk about, which is the incenter. Okay. All right, so talking about finding the circumcenter in the coordinate plane here on page 363, all right, you'll notice that for this first triangle that we're given here, we're given some nice coordinates, right? -6, 0, 0, 4, and 0, 0. And so we come up with this triangle right here, okay? What kind of triangle could we identify this triangle to be? It's right? It's got a right angle there, okay, right? These three. And then also probably scalene, right? In fact, it's for sure scalene because it's 4 there, it's 6 there, and the hypotenuse certainly won't be the same as either of those. It's actually pretty straightforward to come up with the circumcenter for this particular triangle because of the fact that we have a vertical and horizontal side here. Okay, the horizontal side, all we got to do is find the midpoint. So if it's 6 units long, just go 3 in, right, or 3 in from the other side, and then draw a vertical line, right, because vertical is perpendicular to horizontal. Likewise, here we have a horizontal line. And it's a horizontal segment. It's 4 units, so go in 2 from the top or from the bottom, and then again just draw a vertical line, go in 2 from the top, 2 from the bottom, and then draw a horizontal perpendicular line to it. And that gives you the location of the circumcenter right there. Okay? So the distance from this point to S, to R, or to O will be the same. Okay? And you can kind of see it using the slopes, right? To get from this point to S, you have to go up 2, right 3. To get to R, you have to go down 2, left 3, and then to get to O, you go down 2, right 3. And so the slopes kind of give it away that it is equidistant there, but you can also, of course, calculate using the distance formula if you wanted to show for sure that the slopes are that the distance is the same. Okay. Let's try this next one, though, letter B. I don't think they were so kind to us here, but they might have been, so let's see. So letter B, point A is -1, 5. Point B is 5, 5. And point C is 5, -1. Actually, they were pretty kind to us here. Straight edge for this one. Okay. So we actually don't need our compasses here. Could you use them? Absolutely. So if you wanted to at this point, to then do your perpendicular bisector constructions for the sides, that's absolutely fine. Okay? I'm going to go ahead and just draw it in, though, because we have a nice horizontal side and we have a nice vertical side there, so I'm not going to bother using my compass. You could if you wanted to, but it's not necessary. right? So here, what's the length of this side right here? It's 6, right? And so to go to the midpoint would be 1, 2, 3 in, or 1, 2, 3 in from that side. And then we'll just draw a nice vertical line that'll be perpendicular to that point. So there's one perpendicular bisector. And then this one here, 1, 2, 3, 4, 5, 6 units long, so half of that is 3. So we'll count in 3 from each one and do a nice horizontal line perpendicular to that side. And then voila, there is our circumcenter. Okay. Now this is a right triangle by its angles. What is it by its sides? It's right what? Oop. Isosceles. Yeah, it's 6 and 6 there. So yeah, it's isosceles. And so we have this nice perpendicular, or nice circumcenter right there. And if you want to show that is in fact a circumcenter, again, you can draw, put the point of your compass at that circumcenter, adjust it so that it's, you know, the length to one of the vertices there, and then it should kind of okay, voila. Nice little triangle there. A nice little circle there that goes around the triangle. For the most part. I didn't, it's kind of not quite right there. That might have been my finger moving or something like that. Okay? So there it is, circumcenter. All right. Equidistant to the vertices of the triangle, made up of the perpendicular bisectors. Questions on any of that? All right, got one more special center for us here, and that is on the next section. Okay, so the next section we're going to look at now. So if you want to turn to 8.2, I'll give you the page numbers here in just a second. It's going to be on page 371. Okay, so 8.2, page 371. Okay, and actually let's go ahead and go to page 372. We'll skip ahead to page 372. Okay. So at the top of page 372, we have two little theorems here. We're not going to worry about proving them, okay? We are going to mention them here. We have what is called the angle bisector theorem, which states that if a point is on the bisector of an angle, then it is equidistant from the sides of the angle. So in other words here, we have an angle APB drawn with ray PC bisecting that angle APB. Okay? Any point that you select along that angle bisector is the same distance to PB as it is to PA. Okay? And you can see they're using like a kind of the perpendicular distance from PA or PB to point C there, right? So the distance from any point on the angle bisector is equidistant to either side of the angle, okay? All right. Likewise, though, if you go in reverse, so if you locate a point that is equidistant from the two sides of an angle, that point is on the angle bisector, okay? So if we jump down here real quick, so for example, you know, we're told that J to M is 12.8, right? And so we're asked to find each measure. Well, very clearly here that ray KM is an angle bisector. And so if J to M is 12.8, then that means M to L is going to be 12.82, right? Okay. Likewise, you know, right here, we're told that angle ABC is 112 degrees. So this whole angle right here, that whole angle is 112 degrees. Since point D, okay, is equidistant to this side as it is to this side, right? They're both 74. That means these little individual angles, we can cut those in half, right? So this is an angle bisector. Ray BD is an angle bisector because it's equidistant to the two sides. And so we can say that this is going to be, you know, 56 degrees here and then 56 degrees there too. Okay, so these individual angles. So the measure of angle, you know, CBD is equal to 56 degrees, which is half that 112. Okay, so important piece of information there. Okay, any point on the angle bisector is equidistant to the sides of the angle. And so then, let's go to page 373, and we've got ourselves here another triangle. But on this triangle, we're not going to construct the perpendicular bisectors, we're going to construct the angle bisectors. Okay, so I'm going to tear this out, and we'll do that here real quick. All right, so compass, right, pick an angle. I'm going to start with angle P. I'm going to turn my paper so that angle P is kind of like, again, I got PR, it's horizontal there to me, and then P, which is my angle. Compass point on angle P. Might not be a bad idea to put some actual like points on P, Q, and R there. Okay, but let's just do the angle bisector for that angle at point P. So compass point on angle P, swipe to hit both sides. Okay, just like that. And then remember Emma told us during the warm-up that we're then supposed to take our compass and put it on the points where our arc intersected there, and then swipe in from both of those points into the interior of that angle. Okay, so just like that. And then we can draw from P through those little arcs there. Like so. Okay, so there's one angle bisector. I'm going to erase away some of the markings to help me out there. There's one angle bisector. Okay, and now I'll pick another angle. I don't know, I'll do Q. Okay, so I'm going to turn my paper again so the Q is kind of on my left-hand side. I'm right-handed. I like it being on my left-hand side. I don't know, for you guys, you can kind of do whatever you want, how you want to orient things. Just going to point on my compass on Q. I'll swipe to hit both sides there. And then I'll swipe into the interior. And then do the same thing from there. It can get a little bit tricky. There's a lot of different things going on here, so just be careful. Okay, there's where they intersect, right there. Okay. Okay, as you can see, angle bisector, they intersect right there. Okay, if we were to angle bisect angle R, we would see that it would also go through that same exact point. Okay, and so that's why we're not going to worry about bisecting angle R. If you recall back when we were doing the perpendicular bisectors there a moment ago, okay, when we did that one in the coordinate plane, we didn't bother, right, when we did this one in the coordinate plane here, we only did 2 perpendicular bisectors. We didn't bother doing the third one here for this third side. It's because it's not really necessary. Once you have 2 perpendicular bisectors in there, you can find where your point's going to be. You know the third perpendicular bisector will go through that same point. Likewise here, with my angle bisectors, it's not necessary for us to draw all 3 angle bisectors there because you know the third one is going to go through this same exact point where the first two intersect. So it's not necessary to do the third one. If you want to, you can. Okay, now, this point will not be equidistant to P, Q, and R. But what should it be equidistant to? Not the angles, the sides, the segments. Remember, we just got done talking about the fact that angle bisectors, points along angle bisectors are equidistant to sides. So, for example, this angle bisector right here, right, any point along that is equidistant to side QP or PR. Okay? Any point along this angle bisector right here is going to be equidistant to PQ and QR. And so this single point is equidistant to the 3 sides of the triangle. So if I put my compass point on that point that we located, and if I adjust it so that my compass point barely, this is not going to do a great job because it's a little too small for my safety compass here, but anyway. If you adjust your compass, I'll just do it real. Okay, you can see here, and again, because I couldn't quite adjust mine down to be small enough, but you should be able to draw a circle that kind of fits just inside. This didn't quite work the way I was hoping, but okay, like that. And again, I wasn't able to adjust my compass down enough. But again, for you with your compasses, you'd put your compass point on that point, and then open up your compass just so it barely would touch one of your sides, barely intersect one of your sides there. I couldn't open it up quite enough there, or close it down quite enough. But you can see that the circle would have fit right, I think, if I just shrunk it down. Okay. This one's the harder one to get, and I'm not sure why. I always seem to not quite do a good enough job with it there, but it is supposed to be equidistant to the sides of the triangle. Okay? Since the circle that we draw is inside the triangle, we're going to call it the incenter. Okay, the incenter. Okay? It's the point of intersection of the angle bisectors of a triangle. Okay, and is equidistant to the sides. Of the triangle. Okay. The circle is called the inscribed circle because it is inside the triangle. The circle is inscribed in the triangle. And then, of course, the other circle that went around the outside, that was the circle that was circumscribed around the triangle. So the incenter finds the center point of the in circle, okay, or it is inscribed there. And then the circumcenter finds the center of the circumcircle. Circle goes around the outside. Okay. Questions on any of that? All right. So again, if I flip over to the next page there, we're not going to go through all these. I think you guys get the idea. We'll get you some practice on it here, get you started on the homework, okay? But again, just the incenter theorem, the angle bisectors of a triangle intersect at a point that is equidistant from the sides of the triangle. Okay, so there's point P, right? You have here's your angle bisector right there, angle bisector right there, angle bisector right there. And so there's point P, the incenter. And so it is equidistant to the sides. So P to Y, P to Z, P to X. Now those are all equal. I'll mark them in here. Okay, those are all equal to one another. Px, Py, Pz. Point P, the incenter, is equidistant to the sides. Okay, so let me get you guys started on that because I think everything else is looking good there. Yeah. Okay, so let me give you guys your assignment here. Alrighty. And since some of the homework is going to require you to do some constructions, I'm going to recommend that you do those problems first, okay? So I'll kind of list those first. So page 365. Okay. Numbers 1 through 4, just pick 2. I don't care which 2 you do. Okay. And let's see here. And then 8, and on the next section, then, page 376, numbers 6 or 7, just pick 1. Okay, so those are the constructions. So make sure you get those done today before you leave. Okay, you definitely want to get those done before you leave because I can't let you take the tools home because I just don't have enough that I want to do that. But then additionally, I'll add some other problems here too. So then page 366. Number 7. shoot, I also want to do 13, which that's going to require. Sorry, so page 3, I also want you to, I'm going to add on number 13 as well, so don't forget to do that one too, sorry. I do want you to do that. Let me use this one. 10, 11. I guess 19 should go up there. All right. So there it is. I think I've got everything I wanted up there. Okay. I added 19 onto the one I'd like to try to get done here in class today. If you don't get it done, that's okay. You can kind of try and sketch it at home. That shouldn't be too bad, but there's the assignment. I know it's kind of weird, but there it is. Okay, and I'll put that up on the Google Classroom too, in case you're concerned about forgetting it. I'll do that right now. Brendan? Yeah. Yours broke.
Yeah, I have,
Your own. Yeah, I'm sorry.